So the first question is from Fabrizio. Natural language search, language modeling, Google BERT and OpenAI GPT-3, and of course many others, and neural search are extremely popular buzzwords nowadays. But what does it mean to integrate these technologies with an open source information retrieval implementation? For example, what should I do if I want to design and implement a search engine with such features with Apache Solr and, of course, Elasticsearch? So we will answer to this question with an overview, first of all, on what can be considered neural search, what can you do currently with the latest Apache 2C in development, and how you can achieve that kind of experience with Apache Solr and Elasticsearch. So first of all, some general considerations. So in the question, there are mentioned a couple of language models. So first of all, what is it? So what's a language model? So I listed in here a couple of the most popular ones, mostly because BERT, when released, and it was possible, and Google released not only academic papers about it, but also the possibility of downloading pre-trained BERT model. It got a lot of popularity. And this year, GPT-3 got a lot of popularity from like even mainstream media, because there were the possibility of basically reproducing human language and reproducing like human-like articles written by a language model effectively. And I also mentioned in here the Stanford question and answering chart. Basically, it is like a top, the top results from current models in the task, in the natural language task for question and answering. And you'll see in there the results from different models and combination of models, of course. So what is a language model? Normally, they are pre-trained on large corpora, which is a very expensive task. Because for large corpora, we mean, for example, the entire Wikipedia or equivalent. And this is done for having the model to understand like sentences and also the way terms are related to each other. So I was saying that first of all, you need the model to understand human language, and you do that pre-training on large corpora. And then you can do an ad hoc fine-tuning to solve specific natural language tasks. And this activity is much less expensive. So what effectively will do a language model? It will gain the ability of encode terms and sentences as high-dimensional vectors. So you may have an input after you train a model, and is not in scope of this to answer this question, of course, how this model internally works. There are like a lot of papers to describe that. We'll probably follow up with blogs on that, so you will find more details about the internal functioning of these deep learning components in a different session. So let's focus on how you can use a model like that. So you can query BERT, for example, a model through, for example, BERT as a service, and get back from your input query in high dimensional vector. So in this example, you may have different sentences like access the bank, walking by the street, tigers are big cats, and you can get a vector out of any of these sentences. So specifically out of these 3 sentences. So once you have a vector, from a sentence, you can imagine how you can use language model in search. At indexing time, you will be able to encode sentences on full field content, for example, and store the vectors in a data structure that can be used at query time. at query time, you may encode the query and then score a query document vector, calculating some of the possible distances you may be interested in. So you may use the Euclidean distance to calculate how close two vectors are to each other, or the cosine similarity to understand just how close they are in terms of the angle that basically separate two high-dimensional vectors. So this is a very interesting approach in search, because we are moving away from approaches such as BM25 that base their functioning on term frequencies and rarity of terms in an inverted index, to an approach which is quite different, because you build vectors out of fields, you build vectors out of documents, you build vectors out of queries, and then you calculate distance in vectors. And this vector is meant to represent the meaning, the semantic of a sentence, of a term in an high-dimensional space. What are limitations of this approach in general? And then we'll see what happens with open source implementations. First of all, it may be actually quite problematic to rank an entire corpus of documents, because if you need to calculate just the score of each query search result pair, of course you need to traverse the entire corpus of documents. So how this is solved? Normally this is solved through an implementation of approximate nearest neighbor. And what is the performance of the extraction of the embeddings? So the embeddings is like another way you can call the vector extracted and returned by a language model. The results can be unintuitive, because in traditional information retrieval, you may clearly see, like, if a term appears in a search result. With a vector approach, you can't do that, because you have like the representation of a document, the representation of the query is not human readable. So you need to trust the engine, basically, and it's very difficult to explain. It's not easy to explain a search result with this kind of search approach. So how you can achieve neural search, so vector-based search with Apache Lucene, Solr, and Elasticsearch? So first of all, currently, the implementations available imply that you extract the embeddings. So you extract the vectors, and then you just provide the query as a vector, and you provide indexing document as vectors. So we can classify algorithms for like improving vector retrieval more or less in 4 big families. So tree-based algorithms, such as KD3, hashing methods that tends to hash a vector in the way that when you are going to get the vector from the query, you can match similar vectors directly instead of ranking all the vectors, score all the vectors. Product quantization, which is it's similar to a certain extent to hashing, because you are basically like reducing the fine grain of a vector, again, to basically reduce the number of different vectors you have in your data structures in your corpus. And finally, graph-based approaches, which have the objective to basically guarantee like a hierarchical structures that you can build offline and then reuse to reduce the amount of candidates when scoring. In Apache Lucene, in November 2020, so this is a quite recent contribution, we got the hierarchical navigable small world graphs approach implemented and fully contributed. There's also work in progress for EVF flat approach, which is tracked under the Lucene 9136 issue. On top of that, a unified vector format approach for the file format has been contributed in the way that if new approaches are introduced, it's possible to leverage the same data structures. So this is quite an important milestone for vector-based search in Lucene, because it basically gives you the possibility of having a dedicated file format. As we're going to see with the Apache Solr and the Elasticsearch current approaches, they leverage other data structures that were in Lucene and Solr and Elasticsearch before, and they basically just try to reuse them. So of course, it's not complete as a work. So there are a lot of follow-ups that are going to happen in Lucene to reduce the heap usage, because you may imagine that during the indexing time, you are building these graphs that are going then to be leveraged at query time to just explore part of the corpus. So this currently will occupy a huge amount of memory. Then the query side, of course, is missing at the moment. So there are some kind of interval search potentially available, but not really, just to basically provide the approximate neighbor and interrogate the graph, but not effectively like a full query interface. So that's missing at the moment. And additional work, especially benchmark for performance tests, and also benchmark from a search quality perspective on public data sets. So keep an eye on Lucene, and specifically on this Jira, you will get updates. So what's the current situation in Apache Solr? So first of all, the Lucene latest codecs are not available yet, so are not used yet. So they are in Lucene, but they are not used by Solr solutions. There are two Jira tickets that explore that. One, 12.890, which contains a summary and a long discussion that has been going on for a while, and 14.397, which effectively has the scope of developing an official solution for having this working in Apache Solr out of the box and using the Apache Lucene recently contributed approach. Still, there are ways of having vector-based search and basically integrating the language models with Apache Solr. And there are three main methods to do that. A vector scoring using streaming expressions, which rely on point fields. A Solr vector search plugin that has been contributed in the past, and other people have been also documenting usage of it through blog posts, and especially Dimitri, he contributed an 8.6 Apache Solr porting of the plugin, which is usable. And also another plugin that leverage local sensitive hashing. Limitations. So it's not like a panacea for solving everything. It's currently quite slow. So those solutions may not be production ready to performance extent if you have a big corpus. And they reuse data structures such as point fields and payloads in Lucene. And currently, they support just one vector per field. So if you want to model, for example, a big content with multiple sentences, at the moment, you will need to encode the entire content as one vector, while you would ideally like to encode sentences as different vectors. So let's see the first approach, how you can implement this in streaming in Apache Solr. So at index time, you define as a field type, actually this is the default one, which is float point field. And you may reuse the *_fs, which is a dynamic field, which of type pfloats. This is then you can index documents just adding multi-valued fields. So the vector will be encoded as a multi-valued field. So each value of the vector is actually one value of the field, because bear in mind that float point field is unidimensional. So at the moment, unfortunately, we're going to see this is a limitation. You can't have multi-dimensional points, so except for GeoSearch, but that's a different thing. And anyway, you may have just two-dimensional points in Solr. In Lucene, multi-dimensional points are supported. So you can see actually there's a very interesting blog from Elastic talking about losing points. So this is what is used currently with Apache Solr streaming expression and what you need to do at indexing time. At query time, you may run a streaming expression that is going to first run a query. So this is going to reduce the scope of your search results. In this case, in this example, it's just the match all query. And then you can use the cosine similarity function that takes in input the field, and in this case, it's the field we previously populated, and an array, which is the query vector. The response will be a result set where the documents in your corpus are ranked by this similarity score. Now, this is something currently available in Solr 8.7, but first of all, again, it doesn't use the new Lucene file format specifically designed for vector-based search. Then it's not usable in normal search, so you need to use streaming expressions, which may not be something you actually want in your use case. And it requires traversing all the vectors in the search results streamed by the original query. Furthermore, there's no support for multiple vectors per field. Second approach, Solr Vector Search plugin. At index time, what you need to do, you need to create a field type, which is going to be a text field, and the analyzer will have a delimited payload token filter factory, specifically encoding float values. The field name, again, will be like whatever you like, vector, at type, the type you've defined. Then you can push your documents in this format. As you can see, this is very specific to the way the delimited payload token filter factory works. And you usually use, if you don't specify in the filter class definition in your schema, is going to build the payload per term, and the payload will be defined after the pipe after the pipe character. So this means that you need to specify the vectors in your input documents specifically with this format. At query time, what you need to do, it allows you to specify a query through a custom query parser, which is in the plugin, the VP query parser. Specify the field you are interested to apply vector-based search to, and the vector, the query vector. Then currently it supports two possible distances, the cosine distance and the dot product. So if you use the parameter cosine equal false, the dot product is going to be used, and this is going to be the score for documents. So what are the negative points of this approach? First of all, payloads are used for storing vectors, and this is not ideal and it's quite slow. It works, but it may not be fine with your performance requirements. It requires traversing all vectors and scoring them. So that's a quite important drawback. There's also support for multiple vectors per field that must be investigated. It's not clear if this is possible. An important note, Dimitri contributed a port to Apache Solr 8.6 because the original plugin was meant to work with 6.6. Finally, the last we want to discuss for Apache Solr in answer to this question is the LSH hashing plugin. So what can you do at index time? Basically, you need to define a binary field, then some additional fields that are going to store the hashes for the vector. With this specific plugin, you need to specify an update request processor chain that is going to calculate effectively the local hashes for the vector. So in input, you will push documents with a vector where each element in the vector is going to be comma separated. At query time, again, this is an extension of the previous plugin, actually. So you will see the same query parser, and in addition, the parameter LSH equal true. And the re-rank doc, so you may just basically apply this to a subset of your original result set. Now, based on the hashing, so you're not scoring everything this time. Now, performance must be investigated is using a binary field with the encoded vector to float, so that it's using the same encoding that happens for payload. So you need to encode and decode vectors from disk. May not be ideal. The second drawback is the fact that the latest commit for this plugin is dated October 2018. So it's not recent. Now let's see how you can do that in Elasticsearch. So first of all, again, the Lucene latest codecs, effectively they are quite recent because they are from November. They are not used yet by Elasticsearch as well. Still, there is some work in progress for covering approximate nearest neighbor techniques, and this is tracked under this Jira issue. There are also ready-to-use approaches, especially an XPack feature. So this is an enterprise feature, but gives you the possibility of using dense vectors, and a couple of plugins. This plugin has been contributed by the community, and they approach the approximate nearest neighbor problem in a similar way than the Solr plugins that do.
Just a comment about that.
Yep.
It's in the basic. It's available within the basic license, which is free for use. So so you can have that for free, even though it's not a Apache 2 license. The basic license gives you a lot of features for free, like security and things along those lines. And this one is available for free. And you can deploy that within your company, use that in production and whatever.
Perfect. Thank you very much, David, for the clarification. And yeah, exactly. So the source code as well is available, right, David? But under the Elastic license.
Yes, okay. All the enterprise feature, the source code is available as well.
Perfect.
For the basic and the other license as well.
Perfect. So current limitations, performance must be investigated. There are like some studies on those plugins, for example, so you can take a look in there. Limitations that are actually in common with the Apache Solr limitations. So they currently reuse data structures and not the ad hoc codecs and file format recently contributed by Apache Lucene. And also contribute only one vector per field. And that's only supported. So let's see how you can achieve that. At index time, you can use a specific type called dense vector, where you specify the dimension. So the dimension of this vector is the dimension that your language model outputs. So if, for example, you're using a BERT model of an average size, it could return you like 700 roughly dimensions. Potentially, you may use like bigger representational model, and that's fine. You specify this as an input. The additional field is just as an example, like if you are actually building a mapping that contains also additional fields. Then you can push your documents. Quite simple. Your dense vector is just an array of float values. Vectors are internally stored as binary doc values, so that's an important thing to remember. Then, at query time, various distance functions are supported. So you see that from the original documentation that is linked in the previous slides. For example, you may like to use, again, the cosine similarity. And to use that, you may first reduce the scope of your results with a Boolean query or whatever Elasticsearch query you like. In this example, we reduce the scope of our search results to just published status. Then, through a script, you can apply the cosine similarity. And this is going to calculate this score from the query vector in input for all the search results. The syntax is quite simple. It takes in input as a parameter the query vector and the field where you're storing your vectors. Now, we don't go into the details. We don't have time to describe also the plugins from the community that have been contributed for the Elasticsearch approaches, but keep an eye on our blog because we are going to keep discussing on this topic.